Welcome students. We want to discuss about differential equations with discontinuous forcing functions. So again, recall, we had the following differential equation. We had y double prime plus 2y prime plus 37y equals to g of t. Your g of t is the forcing function. And you want to solve this initial value problem. These are your initial values. Y of 0 is 0, y prime of 0 is 0 as well. And your g of t is discontinuous as per the title, because we are studying discontinuous forcing function, and you can see that this is a discontinuous forcing function, right? So now you can write this also as follows. So you can write this function as u1 of t. So we are writing in terms of unit step function. So it is u1 of t minus u4 of t. And if we draw the graph of this function, this is how it looks like. It looks like so from 1 to 4, the function is constant 1, otherwise it's 0. So from 1 to 4, the function is 1. 1 is included, 4 is excluded, and otherwise the function is constant 0. So that is basically here 0 is excluded, and here the 4 is included. So this is how the graph of the function looks like. Yeah. So in this sense, you can think about a constant force. So constant force applied for finite amount of time, for a finite amount of time. It need not be 1. You can scale it up, and still everything else will follow the same way. So let's apply Laplace transform on both sides of this differential equation. So that will be our step 1. Apply Laplace transform on the dE, on the differential equation. If you apply Laplace transform, we'll get the following. So we have Laplace transform of y double prime s plus Laplace transform of 2y prime, so 2y prime plus 37 Laplace transform of y, and all these are having variable s now, is equal to Laplace transform of g of t. And note that this I applied the linearity right away, and that's why I could split it. So let's see, what is Laplace transform of y double prime? So let me write down the formula for that. So this is going to be s square y of s, where what is my y of s? My y of s equals to Laplace transform of y of t. Yeah, it's a standard notation we have been using throughout. Minus s of y0 plus, sorry, minus y prime of 0 plus 2 times. So this is going to be Laplace transform of that is going to be s of 2 times s of ys minus y of 0 equals to plus 37 y of s is going to be equal to Laplace transform of this, and let's call this as, call it g of s. Yeah, just for time being. So this is going to be g of s. The reason why we are doing that is we are trying to work out in general, for without going into specifics of your function g of t, and then in the end we'll apply it to, we'll use the specifics of g of t being this function. So that way you can see how long you can push this procedure for any arbitrary function g of t on the right hand side. So now we are given that this is 0, right? So y of this is 0, this is 0. So this will become 0, 0, 0. So the upshot is, this implies we get take y of s common. So we have s squared plus 2s plus 37 y of s equals to g of s. Right, so we have applied here, this was step 2, we applied we applied initial value, applied initial condition, and then rearranging this, we get y of s equals to g of s divided by s squared plus 2s plus 37. So this is how the form will look like. So now let's see how will our g of s looks like. So g of s is Laplace transform of g of t which is same as Laplace transform of u1t minus u4t, and applying by the linearity, we have this is e to the power minus s, e to the power minus 4s, the whole divided by s. So what is the reason for that? So you can look at table formula 12 from table, and the formula goes Laplace transform of ua of t is e to the power minus as over s. So I'm using this formula. You can do the computation of integral as well to get this in case you want to go about that. So therefore, what do we get? Therefore, we have y of s equals to e to the power minus s upon e to the power minus 4s multiplied by 1 upon, so the s below here, I'm putting it here, s squared plus 2s plus 37. So now to find out solution of this, I need to find out Laplace inverse of this guy, this whole thing. Yeah. So how do we go about it? Generally, it will be okay, but there are these two things here. So we want to basically be able to take Laplace inverse of that. So what we'll do is the following. So this is our 4. Let h of s be 1 upon s squared plus 27s plus 37, which is Laplace transform of some function h of t of s. Yeah, for some s. That is we are saying that is h of t is Laplace inverse of h of s. Okay, so let's have that. So now in that case, we'll have y of t equals to Laplace inverse of y of s, which is going to be u1 of t times h of t minus 1 minus u4 of t times h of t minus 4. Now, this is a crucial step. So because of these guys here, we want to, because of these two here, we will have to approach this problem using u of u1, this unit step functions. Okay, so let's see. So here we got this part now. So why is that? Because if you look at formula 13 from the table, it tells you that Laplace inverse of uc of t times h of t minus c is going to be e to the power minus cs f of s, right? Where what is my f of t minus c, where f of s is Laplace transform of f of t. So to compute the Laplace inverse of this part here, you have to use, yeah. So precisely because of this extra e to the power minus cs, I have to write it in terms of the step functions like that, okay? And then f of t minus c. So let's explore this now. So so we got this now because of that. So now we need to basically use we need to find out. So h of t is what we need to find out. So first of all, we'll write the partial fractions for it. So we want to find out. So so therefore we need to find out h of t, which is Laplace inverse of h of s, to be able to find y of t. Okay. So it all hinges now on finding h of t. So let's embark on that. Okay. So now we have to apply the partial fractions here. So let's take h of s, which is 1 upon s into s squared plus 2s plus 37. This is going to be a by s plus b s plus c divided by s squared plus 37. Now, why is that? Right? Because note we have what? This is quadratic irreducible, right? And consequently, the numerator has to be of form ax plus b, right? If the denominator is a quadratic, then it's irreducible quadratic, then the numerator should be of form, it should be linear. This is what the theory of partial fraction tells us. So now we need to find a, b, and c. So this should give us, we have, let me do that computation in different color here. We have a times s squared plus 2s plus 37 plus b times s plus c times s equals to 1. So this gives me a plus b. So I'm now going to basically organize the coefficient. So what is coefficient of s squared? Coefficient of s squared will come from this part and this part multiplied. So we have a plus b of s squared. Now what about the c term will come from this a 2as plus c. So it will be 2a plus c of s plus 37a equals to 1, right? So a plus b must be 0. So this implies a plus b equals to 0, right? And we get a plus b equals to 0. We have 2a plus c equals to 0. and we have also we have 37a equals to 1. So from there we can get that a, first of all, is 1 over 37. B is, since a plus b is 0, b must be minus a, so minus 1 over 37. And 2a plus c equals to, so c equals to minus 2a, so this is going to be minus 2 over 37. So therefore our h of s is 1 by 37 over s minus 1 by 37. I can take that common. I have s plus 2 upon s square plus 2s plus 37. Now we know L of 1 equals to 1 over s. Therefore, if we apply the linearity here, so therefore we get, this implies L inverse of 1 by 37 divided by s is going to be 1 by 37 s, right? Okay, so now that is not the interesting part. The interesting, or the difficult, rather interesting part is s plus 2, this part here. So how do we deal with this one here? So now to deal with that part, so let's see, how does the denominator, so we need to complete the square in the denominator. So note that s square plus 2s plus 37 is same as s square plus 2s plus 1 plus 36. So we are completing the square, okay, completing the square. Why are we doing that? Because Laplace transform, when the bottom is a square, a square plus b square or s square plus something is easier. It's basically can be read from the table. So this is going to be s plus 1 square plus 36. So therefore, s plus 2 upon s square plus 2s plus 37 is going to be s plus, so I'm going to break the denominator first. So it's going to be 6 square. And on top, so we have, if we'll write it as s plus 1 upon s plus 1 square plus 6. Now, why is that? Why are we breaking it like this? Because recall, so what is Laplace transform of e to the power at of cos of bt? So this is, so Laplace transform of this guy is s minus a upon s minus a square plus b square. And similarly, we have Laplace transform of e to the power at sine of bt is basically b upon s minus a square plus b square. Okay, so now if you look at this, clearly in this case, so therefore Laplace inverse of this part here, so this is same as Laplace transform of e to the power. So instead of a, so here a is what? A is minus 1, right? So we have Laplace transform of minus t, and b is what? B is 6 here, right? So we get e to the power at cos of bt, right? This is what this first expression represents. Yeah, so this is a is -1, b equals to 6. Now in this case, we have, so we need 6 on the top here, right? So we have, so what we'll do is I can multiply and divide by 6, right? So in that case, I'll get plus, this is going to be Laplace transform of, so by linearity, this 6 will come out. So we have 1 by 6 Laplace transform of e to the power minus t, and this 6 will get included because of e to the power at sine bt is b upon s minus a square plus b. So this is going to be sine of, so 6, so this is 60. All right, so we get, therefore, h of t is going to be Laplace inverse of this h of s. Now, first part is, for the first part here, so now we have Laplace inverse of this part, this part. So Laplace inverse of that is, we've already found out here to be 1 by 37 Laplace inverse of this. So Laplace of 1 is 1 by s. So Laplace of 1 by 37s is going to be 1 by 37. Yeah, sorry, I made an error there. Now that should be fine. So this is going to be 1 by 37 for the first part here. Now for the second part, what do we have? We have 1 by minus 1 by 37 outside as it is. Bracket. We get e to the power. Now the first part, so now we want to talk about Laplace transform of this part here. So for that, we have broken it into two parts, as you can see in here and here, that it's going to be e to the power, so it's going, first part is going to be e to the power minus t cos of 60. And for the second part, we have plus 1 by 6 e to the power minus t sine of 60. Yep, this is good enough as an answer. So, and y of t is u1 t h of t minus 1 minus u4 t h of t minus 4. So this is good enough as an answer. However, if you want to proceed further and see y of t, how does y of t looks like really? So you have y of t is u1 t. Now h of t minus 1 is essentially this function, but instead of t, you have t minus 1. So let me write that down. 1 by 37, 1 by 37, bracket close, e to the power minus t minus 1, cos of 6 of t minus 1, plus 1 by 6, e to the power minus t minus 1, sine of 6 of t minus 1. So this is just the first part, u1 h1. Now minus u4 h of t minus 4. So again, the same story, 1 by 37 minus 1 by 37 in bracket. So let me make sure what brackets are. So these are the bigger brackets. plus u4 of this guy. So make this bigger brackets here. And then inside we have smaller brackets, e to the power minus t minus 4 cos of 6 times t minus 4 plus 1 by 6 times e to the power t minus 4 sine of 6 of t minus 4. Yeah, but already here is already good enough as an answer. Okay. So this is how you use Laplace transform to solve this differential equation. Now think about it, it's already an interesting idea, right? Because you have a discontinuous forcing function. None of the techniques we have learned before, the Laplace transform, will be applicable here. So now let's try to understand the solution a bit. So what happens to the solution? Okay, so the different, so this is how the solution looks like. Y of t, so this is your y of t versus t. Now, the different behavior of this function can be characterized into three regimes or three parts, namely the following. First part is this part. Yeah. Second part is all the way until 4. And then the third part is this part here. Okay, so let's analyze our discussion now. So what happens to the solution? So if 0 less than t less than 1, then both the initial conditions are 0 and the system is at rest. As you can see, the system is indeed at rest. Right here, the system is at rest. Yeah. So we have, since we have what, u1 equals to u1 prime. So u1 is 0, u1 prime is 0. So we get this implies y of t is 0. But hold on, we are not talking about this u1 here, we are talking about this. So you can look at this function here. So let's analyze the function from here now. So you see that u1 is going to be 0 in this part, right? Because u1 only becomes positive after 1. So u1 and u4 both are 0. So I should say u1 and u4 both are 0 in this region, right? Therefore, this implies y of t is 0. Okay. So let's call this as this part as, let us label it as y1t. For this part, y1t equals to 0. Now, second part, when you have the forcing function. So here, the forcing function is active. So we have the external force is 1. So we have what, in this case, we have y double prime plus 2y prime plus 37y equals to 1 in this interval. And is the solution. And what do we get? If yt is a solution, to this IVP in this interval with y of 1 equals to y1 prime equals to 0. So we get what this, let's call this as basically the solution is then in that case, let's call this as y2. In that case, what we'll have is, we'll have y of t. In this region, what happens? Your u4 is t is 0 and u1 t is 1. So when you look at this solution now, here u4 part will disappear completely and you will be left with the first part. So in that case, the solution looks like y of t equals to 1 by 37 minus 1 by 37, again e to the power minus t minus 1 cos of 6t minus 1 plus 1 by 6 times e to the power minus t minus 1 times sine of 6t minus 1, and then the bracket close. So this is your y of t. Why is that? Since u4 is 0, right? Since u4 is 0 for t less than 4. Okay, so that part becomes 0. Now we are in the third part here. That means if t is greater than 4, greater than equal to 4, so we are solving. So in this case, it satisfies, the solution satisfies the solution satisfies d y double prime plus 2y plus 37 equals to, again, now after that, so you see the forcing function basically in this range, in this interval, it is 1, and after that it becomes 0. And before also in this interval, it's 0. So that's what I did here. So now we have this equals to 0 for t greater than equal to 4. The forcing function is 0. Now you are given by what? The initial condition is given by what are the initial conditions in this case? Given by y2. So let's call this solutions as y2 with solution y2 given by y2 at t equals to 4. Yeah, that is y2 4 and y2 prime of 4. So you have to basically go and look in this equation, what is the value of function at 4 and what is the value of derivative at 4. So that will give you the y2, and I've already done that computation. So y2 is roughly 0.2, sorry, 0.0263, and y2 prime 4 is minus 0.00623. And if you look at this guy here, this is IVP for a damped free oscillation, right? And it approaches 0 exponentially. Yeah, why is that? Because look at the look at the characteristic equation. Yeah, characteristic equation of this is going to be, you have r square plus 2r plus 37, and we have already seen that's going to be r plus 1 square equals to minus 36. So we get r equals to minus 1 plus or minus 6i. So you see, because r is negative, it will basically force the whole thing down, as you see here, and it will converge to 0 exponentially. So this is a discussion about, this concludes our discussion about discontinuous forcing function of this type. All right, and this can be generalized further to special classes of discontinuous forcing functions. Thank you for your attention.